So, in this particular lecture we will look at moving shocks. This is slight difference from stationary shocks, which was what we were analyzing in depth till now. We derived the expressions for the pressure ratios, temperature ratios of the shock. Also looked at the Hugoniot, which is an expression which relates the thermodynamic variables across the shock, and also how the normal shock equations are applied for the case of flow measurement in a P2 in supersonic flow. In supersonic flow, a shock always stands ahead of the P2. So, one measures the stagnation pressure after the shock and not the stagnation pressure of the free stream. This is an important concept one has to remember. So, that was about stationary shock analysis. Now, let us look. There are several cases where one can find shocks moving. Examples are in the shock tube, and which is a device used for many applications, and the other one is during explosive events, which generates a blast wave. A blast wave is a shock wave that moves in all directions. So, you can look at these schematics. What we normally consider till now is that of a stationary shock, okay, that is fixed shock. So, in a fixed shock, what is happening is you are already having a supersonic free stream. The supersonic flow is happening, and the shock wave stands at a particular location. It is fixed, and the flow gets processed by the shock wave, and you get lower velocities, higher pressure, temperature and densities across the shock. And in contrast, if one looks at the case of a moving shock, here the shock moves with a velocity w, and very clearly this shock can move only at supersonic speeds. So, the velocity of shock wave, that is w, will be greater than the acoustic speed in that medium, which is in this, it is moving into region 1. Region 1 is the quiescent medium here. It is stationary, so it is stagnant. So, it is moving into the stagnant medium. So, the acoustic speed there is a1, and w is greater than a1. So, this must be very clear to all of you. Now, as this wave moves into the medium, it also induces a mass motion. So, there will be a movement of gas behind the shock wave, okay, though that is very different from any normal wave motion that one describes, where we say that particles behind, or as a wave passes, once it has passed, the particle will still remain at the same position, but in a shock wave it grabs the flow, the fluid, and there is a mass motion induced by the moving shock, and you get a speed u2. Sometimes it is also referred to as up, that is u piston. This u piston terminology is coming from the piston analogy that we had discussed very early classes of normal shocks. So, other representations are u2. Okay. So, how do we analyze this moving shock? So, this follows from the principle which is very often used in flows, that if you have a body moving in a flow with a velocity v. So, if this is moving with velocity v in a fluid, an equivalent problem is it is the same as saying that the body is stationary and fluid on the other hand is moving with velocity v in the opposite direction. Okay. So, it is the same problem, it is a transformation. So, you are doing the transformation by applying the velocity v in the opposite direction of the motion of the body. So, same way the moving normal shock can be analyzed by taking the same velocity w and imposing it on the opposite direction. So, once you impose it in the opposite direction, then the moving normal shock gets converted into a stationary normal shock with respect to this stream of gas. So, this is the moving normal shock is in the laboratory fixed frame of reference, while stationary normal shock is in moving frame of reference. So, there we have induced the motion, or we have applied a motion in the opposite direction. So, we have applied a transformation. That means whatever was up over here now gets converted to w minus up, right. So, now how do we apply the equations of shock? So, now we have applied the transformation, now it is a stationary normal shock. So, one can apply the equations of conservation, it is a steady shock wave now. So, you can apply the same equations of conservation rho 1 u 1 equal to rho 2 u 2, p 1 plus rho 1 u 1 square equal to p 2 plus rho 2 u 2 square, and h 1 plus u 1 square by 2 is equal to h 2 plus u 2 square by 2. So, you can apply the same equations. U 1 is the relative velocity, that is upstream of the shock wave, and u 2 is the relative velocity downstream of the shock wave relative to the shock. So, that is, you change the frame of reference to the shock. So, now we know upstream of the shock u 1 is equal to w, and downstream of the shock the relative velocity with respect to the shock is w minus up. So, we can write these equations in terms of w and w minus up, w here and rho 2 w minus up mass conservation, p 1 plus rho 1 w square is equal to p 2 plus rho 2 w minus up square is momentum conservation, and h 1 plus w square by 2 is equal to h 2 plus w minus up square by 2. So, this is energy conservation. Okay. So, these equations are the same for a stationary shock wave. We can go ahead and do an analysis very similar to what we had done for the Hugonoit equation, because you can then take out the information of velocity and look at what is happening to the thermodynamic quantities across the shock. The development is very similar. So, we will just brush through this. So, this is the mass conservation, where you can express w minus up in terms of w and rho 1 by rho 2. From here, and useful expression is up is this up now is in fixed frame of reference or laboratory frame of reference is nothing but w into 1 minus rho 1 by rho 2. So, this is a useful expression, we will come to this soon, and the combination of the mass conservation into momentum conservation and applying similar principles that we express w square in terms of pressures and rho 2 by rho 1 ratio of difference of pressure and density and rho 1 by rho 2 giving w minus up square, and then putting this into energy equation and coming up with the final expression for Hugoniot. So, this is the Hugoniot expression for moving shock. written relative to the shock wave, and it is the same as the stationary shock. So, the shock properties do not change, that is the thermodynamic variables, pressure ratio, temperature ratio, density ratio do not change across a moving shock when we analyze the shock relative to the shock wave itself. So, this is very important whenever you look at problems on moving shocks. Always remember that the analysis proceeds that you first change the coordinates to come on sit in on the moving shock, then the equations are written so that it is relative to the moving shock, and that transforms this into a stationary shock analysis, and you can proceed to get all the variables according to the stationary shock. So, this is a very important principle. So, now let us see how we can express all the different quantities. We are particularly interested in what is this gas motion, how much of this movement can be produced because of a shock moving, and to do that we use expressions from the Hugoniot, where all the ratios T2 by T1 and rho 2 by rho 1 can be expressed only in terms of P2 by P1, where P2 by P1 is nothing but the strength of the shock. Okay. So, now if you do that and you express the Mach number of the shock is always so W by A1, which is A1 is the medium into which the shock is moving. So, MS is the Mach number of the shock. Mach number of shock is W by A1, this is always greater than 1, and P2 by P1 now is given by this expression, which is the same for the stationary shock also, but now this is for a moving shock, and from here one can express MS in terms of the ratio P2 by P1. So, so pressure ratio of the shock and the Mach number of the shock wave, they are related to each other. So, then we come to how we can express the speed of the gas moving behind the shock. So, to do that we use the expression from the continuity equation, which was represented there. UP is W multiplied by 1 minus rho 1 by rho 2, and W is MS multiplied by A1, and you can express this rho 1 by rho 2 in terms of P2 by P1. Then you come to this particular equation for UP, which is expressed in terms of A1, which is the speed of sound in the medium into which the shock is going, and P2 by P1 and gamma. So, this is what is obtained. So, you can use this expression. So, P2 by P1 is expressed in terms of shock Mach number. Now, the Mach number for the induced motion will be with respect to the medium behind the shock wave, that is when the shock is moving here into this medium. This is A1. As the shock moves into it, it produces a motion UP, and across the shock temperature will increase. So, T2 will be greater than T1. As a consequence, A2 will be greater than A1. Right. So, what is MP, that is or M2 behind the shock is actually UP by A2. So, UP by A2, that is, this is with respect to fixed frame of reference, that is with respect to the laboratory, and it is expressed as up by A2 is up by A1 multiplied by A1 by A2, and A is square root of gamma RT. So, this turns out to be square root of T1 by T2. So, if you substitute that, you get this expression solely in terms of the strength of the shock P2 by P1. This is the motion of the gas. Okay. So, now let us take the limit as we had done previously for very large shock waves. So, let us consider a very strong shock wave as infinitely strong shock wave. P2 goes to then P2 by P1 goes to infinity, that we had seen that as Mach number goes to infinity, P2 by P1 goes to infinity. But we also saw that M2, that is Mach number downstream of the shock, goes to finite values as M1 goes to infinity. That means the gas motion behind the shock will also reach finite value. So, let us see what is that number. If you put the appropriate limit in this expression, P2 by P1 tends to infinity, then you get square root of 2 by gamma multiplied by gamma minus 1. Okay. So, this is the expression, and now if you substitute gamma is 1.4, you get up is 1.89. So, that means for a very strong shock wave, the Mach number of the gas flow behind the shock wave is nearly 1.89. It is supersonic, it is very high speed, and so it is not a very small velocity, it is very high velocity flow behind a strong shock, and it can carry huge amount of momentum along with it, and that is what affects bodies once shock waves besides the jump across the shock wave. Now, whatever we have discussed till now, it was on pressure ratios, temperature ratios across the shock wave of a moving shock, and to analyze this, the simple technique was to jump onto the shock wave, a moving shock wave, and write the equations relative to the shock wave, and that renders the shock stationary, and you get all the relations for various quantities. But what about stagnation properties? So, we know from our understanding of the stationary shocks that it is a case of constant stagnation enthalpy, because it is an adiabatic flow. But what about moving shock waves? Now, we had done a change of reference, but the stagnation temperatures and stagnation pressures, they are all to be calculated in reference to the fixed frame, that is the laboratory frame. So, if you do that, first thing that you notice is that H2, that is the enthalpy behind the moving shock, is greater than H1, is what you would get. This is from the shock analysis itself. Not only this, you also find that UP is induced, there is a gas motion induced within the after the shock passes through the medium. Now, the shock is moving to quiescent medium, that means before the shock moves the velocity is 0, but once the shock passes over a particular point, the gas is moving over that point at that point with the velocity up. So, the total enthalpy now is H2 plus up square by 2. So, this is definitely greater than what you had started with initially. So, you find that H02, so H1 is what you started initially, because there was no gas motion. we find that H02 is greater than H01. So, this is very important. So, the stagnation properties for a flow behind the moving shock wave should not be calculated using normal shock relations for a stationary shock wave, but they have to be calculated separately once you have calculated the motion of the gas behind the shock wave. Now, is there any contradiction? We should ask this question, if there is any contradiction or not. It is not a contradiction, because we are actually looking at a case of unsteady flow. If you look at a particular point in that flow, it is not a steady flow anymore, because the pressure temperature changes immediately as a shock passes over that particular point. So, it is not a steady flow problem. So, when it is not a steady flow problem, if you look at the energy equation, then you find that on the right hand side, of course neglecting any heat addition and other terms, on the right hand side you have the term related to unsteady pressure, dou P by dou T. In a steady flow, dou P by dou T is 0, because it is a steady flow, and as a consequence you get in adiabatic flow H naught is constant. Okay. But in moving shock wave, which is an example of an unsteady flow, dou P by dou T is not 0. As a consequence, H naught is not constant. So, that one should bear in mind. So, static properties you across a moving shock is calculated using stationary normal shock relations by doing an appropriate transformation by jumping onto the shock and moving with the shock, but stagnation quantities have to be calculated separately by knowing the properties velocity, temperature, pressure in the fixed frame of reference. Now, let us see, often what happens is that you have the shock wave moving, and it moves and there is a gas motion behind it, and it comes and hits on a solid surface. Okay. So, it can be in the case of a shock tube, or it can be otherwise also. You have rigid bodies which do not allow any motion through them. Therefore, the only way this can go about is that this shock goes and hits the end wall and reflects back. So, you have a reflected shock. Now, the reflected shock is also a moving shock. So, the analysis of reflected shock follows similar lines as the analysis of the moving shock itself. But now you see the boundary conditions, or the conditions that you have to apply, have changed. First thing is that the boundary condition at the wall is that the velocity should be 0. That means, at these conditions, at these places, the velocity is 0, V equal to 0. This term U5 is used here, it is coming in from shock tube terminology. We will come to it soon, but velocity here is 0. Now, this is a relative motion which is happening into a flow which is coming opposite to H. So, the relative velocity here is actually WR plus UP. So, you would impose a velocity WR in order to be on the shock, and that means the total velocity coming on to this shock to make it stationary is WR plus UP, while V is 0. So, behind the gas the velocity is WR. So, this is the problem that has to be analyzed, and so relative to the reflected shock, upstream velocity is Wr plus up and downstream it is Wr. Same set of equations now written in terms of Wr plus up and Wr, and reflected shock Mach number is Wr plus up by 82. Okay. So, in order to make it stationary or to bring it into the stationary frame of reference. So, Wr plus up by A2, and this can be related to the incoming shock itself, that is Ws. The Wr and Ws can be related to each other, and one can express the reflected shock completely in terms of the incident shock Mach number itself. Okay. So, this is a single relation which relates reflected shock wave with that of the incident shock wave. So, if one is to look at what is happening for a particle, so as the very close to the end wall, so as the shock wave coming moves into the medium, it takes all the gas and moves it along with it with a speed up, and then after that the primary shock comes, reflects at the end wall and then goes back. As it goes back, it converts all this to a velocity equal to 0. So, it again becomes the velocity of particle again becomes 0. So, but if you draw the motion of the particle in a xt diagram, that is how it is moving in x, I mean in time and its location in x, then you see before the shock arrives it is not moving, right, and the moment the shock arrives due to the induced gas motion it starts moving with a speed up, and the moment the shock reflects and it comes back and meets the reflected shock, after that it becomes stationary again. But see that there is a fixed motion of the shock of the particle due to the combination of shock wave and reflected shock wave. So, the key ideas here that are introduced in this analysis of moving shock wave is that to analyze moving shock waves, all one has to do is sit on the shock and look at the motion of air relative to the shock wave. That makes the system of equations same as that of the stationary shock. So, the analysis of flow properties, static properties across the shock, moving shock is the same as that of the stationary shock, but always make sure that you do the correct transformation. Again, when one is looking at the gas motion behind such moving shocks, again make sure that the transformations that you apply are correct. So, if you analyze using the normal shocks, stationary normal shock, the Mach number after the shock that you get is relative to the shock wave. So, we should always see to get the velocity with respect to fixed laboratory frame, we again use the transformation back. Then these shock waves, moving shock waves can go and reflect from end walls, and the correct boundary condition there is that once it reflects in such a way that the flow after the reflected shock passes over is 0, because flow cannot penetrate inside the wall. And analysis of the reflected shock is again same as a moving shock, but now the coordinate transformation or the transformation is Wr plus up, which is what you have to take care of. So, moving shocks are important in shock tubes which are devices used in several laboratories and having other applications as well. It is a case of an unsteady flow. So, we will discuss, we are now discussing 1D flows. So, we will discuss unsteady flows in the coming classes. Before we do that, let us solve some numericals in the next class to get the concepts of normal shocks more clearly.